Hello, welcome to MSE 245, Semiconductor Characterization. Today I'm going to discuss the first part of optical characterization, and that is optical microscopy. A material scientist or a researcher may find optical measurements to be attractive because of the non-contact method and minimal sample preparation. Contacts can damage the structure of samples. In many cases, you may want to preserve a pristine sample surface, or you only have a precious number of samples. Another attractive thing about optical measurements is that the techniques are commercially available. The instrumentation is automated. Now, this slide shows the main optical techniques. When light of certain energy h nu is made incident with the sample surface or interact with the sample, it is either reflected or absorbed, transmitted, or emitted. Under each of these descriptions of the behavior of light are specific optical techniques. For example, for photoluminescence, it means that you characterize your sample in terms of the emitted light. In the case of ellipsometry, you study the reflection of the light. You study your sample in terms of the reflected light. Now, a key element in optical characterization is light, and we know that it is a broad spectrum. So we have to be clear that optical measurements use the ultraviolet to the far infrared region of the electromagnetic spectrum. The important parameters are wavelength, energy, and wave number. The common units of measurements are nanometers, angstroms, micrometer for wavelength, electron volts for energy, and inverse wavelength for wave number. The equation showing the relation between energy and wavelength is shown. E equals hc over lambda. Let's draw our attention on the photometric measurement. We are concerned here with the amplitude of the reflected or transmitted light. The factors that come into play are the optical constants such as the refractive index and the absorption coefficient. The photo shows a picturesque view of the Grand Canyon. We can see this side of the mountain and some people on top. We can also see clearly this side of the mountain on the right. We notice that these parts are more visible than the other parts in the photograph, especially that part on the horizon. In appreciating such scenic features of a vista, visibility is affected by absorption coefficient and refractive index. Radiation or information on image formation originates from the landscape features and is scattered and absorbed as it passes through the atmosphere toward the observer. Refractive index is defined as the ratio between the speed of light in vacuum and the speed of light in a medium of greater density. The absorption coefficient describes the intensity attenuation of the light passing through a material. In a place like the US, people have a visibility program, which is part of an effort to take care of national parks. Some of the activities are monitoring of the atmosphere, modeling, and controlling of visibility-reducing particles. Visibility is concerned with the observer being able to appreciate features of a landscape. For instance, why do distant mountains appear bluish? It is because very little light from the mountains reaches the observer. The second category of optical measurement is interference measurement, wherein the phase of reflected or transmitted light is determined. This phase gives information about the film thickness and the surface structure. Here is how. On the right, we have a schematic of a sample with two types of layers. Okay. The purple layer has an index of refraction N1, and that layer is on top of this layer, the gray shaded layer. The index of refraction of the purple layer is greater than the index of refraction of the surrounding air. The light travels in these two media. Here we see the light represented by the red arrow. It strikes the upper surface of the sample, and it is either reflected or transmitted. The transmitted light strikes the bottom surface of the purple layer, and it is again either reflected or transmitted. The reflected rays from the upper surface and bottom surface interfere. Okay, they have a phase shift. When the two waves are in phase, they create constructive interference. However, if the two waves are 180 degrees out of phase, then the two light rays create destructive interference. If the deposited film, the purple layer, has a thickness that is a quarter of a wavelength, then the total path difference of the light rays is half a wavelength. That means that the light rays are half a cycle out of phase. The result is destructive interference. So the resulting pattern is light and dark bands. Aside from that, a possible pattern is a colorful bands, shown by the photos on the left side. Okay, the photo on the left shows interference fringes, indicating that the surface is not flat. These are light and dark rings called Newton's rings, which occur, for instance, when a lens that is flat on top and slightly curved on the bottom is placed on a flat plate and then illuminated with monochromatic light from above. The type of interference that occurs when light is reflected from a thin film is dependent upon the wavelength, the angle of incidence, the thickness of the film, the refractive indices of the film, and then the surrounding media. Back to the photo on the left side. We have here fuel on top of water, creating a thin film, and the thin film interferes with the light, producing different colors. The different bands of colors represent different thicknesses in the film. This phenomenon is what we call thin film interference. Now in this slide, the photo on the left shows two waves A and B that are out of phase. Okay, notice that for wave A, this is one full cycle, and we notice that wave B is half a cycle out of phase with respect to wave A. The result is the black solid line, letter C, okay, indicating destructive interference. In contrast, the photo on the right side, we have waves A and B that are in phase, resulting to wave C, which has greater amplitude, which has increased amplitude. Okay? This indicates constructive interference. Now, this photo at the bottom shows colorful bands due to interference of light with oxide film of varying thickness. So, interference measurements is good for film thickness and surface structure. Furthermore, here is a photo of a lovely blue morpho butterfly. The microscopic ridges on the wings interfere with the light, producing the beautiful blue color. Next, light waves are transverse waves. Polarization of light demonstrates this fact. A polarizer is defined as an optical filter that lets light waves of a specific polarization pass through while blocking light waves of other polarizations. The H sheet is a polyvinyl alcohol PVA polymer impregnated with iodine. The PVA polymer chains are stretched such that they form an array of linear molecules. The iodine attaches to the PVA molecules and makes them conduct along the length of the chains. Light polarized parallel to the chains is absorbed, okay, as indicated by the red wave, while light polarized perpendicular to the chains is transmitted, okay, represented by the blue color. If the source of the electromagnetic waves is vibrating electrons, the plane polarization of the light waves depend on the direction of acceleration of said electrons. A vertically accelerating electron produces vertically polarized light. However, remember that common light sources are unpolarized because there is no preferred vibrational direction for the accelerating electrons emitting the light. Recall that light is emitted radially, so imagine numerous planes of vibration. We can represent these planes by radial lines, or better yet, simply by horizontal and vertical components. We represent unpolarized light by horizontal and vertical components. When there is a polarizer, one component of incident unpolarized light is absorbed, resulting in emerging polarized light, such as circular polarization and elliptical polarization. Recall that the electric field vector vibrates in the direction perpendicular to the propagation. Circular polarization is a polarization state in which at each point the electromagnetic field has a constant magnitude and is rotating at a constant rate. In elliptical polarization, the electric field vector describes an ellipse in any fixed plane, intersecting and normal to the direction of polarization. In a real-world scenario, as simple as viewing a distant part of the highway on a sunny day, natural light is unpolarized. When the sunlight is reflected from an insulating surface like the highway, it is now polarized light, with an electric field vector vibrating in a direction parallel to the ground. And so to prevent glare, you wear a sunglass with polarizing filters oriented in the vertical direction, okay, to block the light polarized parallel to the ground. In the next example, you can achieve these effects when you use two polarizing filters on unpolarized light. In the top figure, the second polarizing filter could have its axis parallel to the first polarizer, or it could be rotated so that only a part of the light is passed. Okay? In the bottom figure, the second polarizing filter has its axis perpendicular to the first polarizer. Hence, there is a dark area. We have here another example of the polarizing filter effect. In the case of thin film iridescence in butterflies, colored light from thin film iridescence in butterflies is often polarized. Here, the left wings are unmodified, while in the photo, the right wings were generated by taking two photographs through a polarizing filter that is rotated by 90 degrees between exposures, and then producing the difference of the two images. So we have a pattern of polarized and depolarized regions. It is known that the wing color of butterflies is important in male attraction to females. We move to another topic related to the interaction of light and diamonds. We ask the question, what's so special about diamonds? Total internal reflection coupled with a large index of refraction explains why diamonds sparkle more than other materials. The critical angle for a diamond to air surface is only 24.4 degrees. And so when light enters a diamond, it has trouble getting back out. Facets on diamonds are specifically intended to make this unlikely. And so the light can exit only in certain places. So we've covered the examples of optical measurements. At this point, let's consider the definition for microscopy and optical microscopy. Microscopy is a technical field of using microscopes to view samples that are not within the resolution range of the normal eye. Optical microscopy involves the diffraction, reflection, or refraction of electromagnetic radiation with the specimen and the subsequent collection of this scattered radiation in order to create an image. Shown is a photo of an optical microscope. In optical microscopy, the illumination source is a beam of photons. And this type of application is limited by the diffraction limit of light. The following are the parts of the optical microscope. 1, ocular lens. 2, objective turret. 3, objective. 4, coarse adjustment. 5, fine adjustment. 6, frame. 7, light source. 8, diaphragm and condenser lens. 9, stage. Let's start with the light source. So again, we use the photons to illuminate on the sample. And then we have the condenser lens. Here it's number 8. The condenser lens gathers light from the light source and concentrates into a cone of light that illuminates the specimen. So the specimen is positioned here on the stage. And then the objective lens. This is used for specimen visualization and it has magnification power. And then the ocular lens, it is also called eyepiece and it is used to look through the microscope. We have to understand image formation. We're going to use an optical microscope. The convex lens shown has been shaped so that all light rays that enter it parallel to its axis, this one is the axis, cross one another at a single point on the opposite side of the lens. Okay, again, the axis is defined to be a line normal to the lens at its center. Since the index of refraction of the lens is greater than that of air, the ray moves toward the perpendicular as it enters the lens, and it moves away from the perpendicular as it exits the lens. The point at which the ray crosses is defined to be the focal point F. The distance from the center of the lens to its focal point is defined to be the focal length, small f, focal length of the lens. So here is how the image formation is applied in understanding the anatomy of a light microscope. Now, light is an electromagnetic wave and a particle as well. Having a wave nature, the light waves interfere with one another, causing a limit to the performance of microscopes. Light bends when there is an obstruction. For diffraction at a circular aperture of diameter d, the angular position of the resultant wave is given by sine theta equals 1.22 lambda over d, where lambda is the wavelength of light and d is the diameter of the aperture. This is the equation for the Wiley criterion for angular resolution. The second equation describes the spatial resolution by a lens, while the third equation describes the resolution for microscope objectives. Here, the figure depicts further when light is diffracted by a circular aperture of diameter d. In the resulting diffraction pattern, the circular spot contains most of the light. This circular spot is what is called the airy or the diffraction disk. The same kind of pattern is formed when a point is imaged by a microscope. So when you have 2 point objects a distance s apart, overlapping images can be produced, as shown in this figure. If they are too close, it is impossible, as shown in this figure, to resolve them. It's impossible to resolve them. Wiley suggested that the two objects can be distinguished when the central maximum of one coincides with the first minimum of the other, such as what this image depicts. There is no limit to the size of an isolated object that can be detected given sufficient illumination. Equation 10.3 in the textbook, or the separation S, the minimum separation S, gives the resolution. Okay, it's the minimum distance between points or parts of an object that satisfies Wiley's criterion. The numerical aperture, usually engraved on the objective mount, is a number expressing the resulting power of the lens and the brightness of the image formed. Notice that resolution is inversely proportional to the NA, numerical aperture. Now, under optical microscopy, we cover bright field microscopy, dark field microscopy, and interference contrast microscopy. In bright field microscopy, the light impinges vertically on the sample. Horizontal surfaces reflect most of the light, while slanted or vertical surfaces reflect less. In dark field microscopy, the light impinges at a shallow angle on the sample. Light from horizontal surface does not reach the lens, but light from the slanted and vertical surfaces does. The image contrast is the reverse of that of bright light imaging. It is depicted by these two photos. Okay, the dark field image is a reverse of that of bright light imaging. Furthermore, dark field microscopy is especially useful to bring out small surface irregularities, which are difficult or impossible to see with bright light microscopy. Dark field microscopy is akin to seeing dust in the air in a darkened room when bright sunlight falls into the room, scattering light from dust particles. Now, our book by Schroder has a good discussion about phase contrast microscopy and interference microscopy. In interference contrast microscopy, the system allows for appropriate phase adjustment for optimum contrast. Both edges of a raised portion of a sample can appear bright against a dark background or dark against a light background for monochromatic light. And step heights as small as 3 nanometers can be observed, making this technique suitable for measurements of planarity of surface, of wafer surface, and then for etch pit studies. The magnification N is related to the resolving power of the microscope objective and the eye. Resolving power is the ability to reveal detail in an object by means of the eye, microscope, camera, or photograph. The equation M is given by the maximum numerical aperture of microscope divided by the minimum numerical aperture of eye. So we have here the values 1.4 divided by 0.002 equals 700. M is also derived by using the limit of resolution of the eye divided by the limit of resolution of the microscope. In this case, we use the numbers 200 micrometers divided by 0.61 lambda divided by numerical aperture. Here, the eye resolution is related to the distance between the rod and cone receptors of the retina of the eye. It was mentioned a while ago that the limit to optical microscopy is the diffraction limit. Diffraction limits the smallest possible spot diameter. So this limit belongs to what is called conventional microscopy. Conventional microscopy images the far field. There, the Rayleigh limit prevails. However, there has been improvement, such as what is offered by near-field microscopy. Near-field microscopy images the near field. The resolution is determined by the aperture, not the wavelength. Let's look at the following schematic to understand those concepts better. On the left, we have a figure describing the conventional microscopy. So light beams are diffracted by the lens, and this is the resulting spot diameter, the spot size, delta x, which is dictated by the diffraction limit. So here it's lambda over 2. And then let's go to the figure on the right. The light beams are also diffracted by the lens. And notice that photons are transmitted through an aperture of size D. Okay? This is now the near-field microscopy, which is no longer limited by the wavelength of the light, but by the aperture size. Furthermore, in the figures, we have components of the waves of the transmitted photons, the spherically diverging wave, and then the evanescent wave. So again, in near-field microscopy, the light is confined to a small aperture. And so to give more opportunity to appreciate the topics on optical measurements, we have here an activity entitled Photo and Micro. Thank you for your attention. Stay safe, healthy, and awesome.